Hello, everyone. Thank you for your patience. Welcome to the stream today. This is our second August stream, and we are excited to be here with you. My name is Matthew. I am one of the course staff and the instructors for our online astronomy classes on Coursera and Udemy. And we are going to get started with your questions today. Professor Impey will say a quick hello, and then we'll get right into your questions, which you can post in the stream. Post in the chat, and we'll grab them from there. Please ask your questions only once. And we tend to jump around to get a variety of topics and a variety of participants. So we see them all, and we appreciate your patience. So go ahead, Chris, welcome everybody, and then we'll get started with questions.
Sure. Hello, everyone. I've got a bit of a late start here, so we'll get right into it. Your floor is open for questions on astronomy.
The first question is from Abiha Faisal, who sent an email asking, why is the universe expanding, and what role does the gravitational force of attraction play in the expansion of the universe?
The expanding universe is a continuing event, if you like, that was initiated by something we call the Big Bang. And the Big Bang is the origin of the universe 13.8 billion years ago in a very hot, dense state. And the universe has been expanding ever since at a rate that's varied over time. So the cause of the expansion is the Big Bang. In other words, there was energy input into space-time back then to make it be expanding ever since. The role of gravity in that is interesting because gravity also obviously is an attractive force, and the universe has mass and energy in it, and that mass exerts gravity. And so all the objects in the universe, stars and galaxies essentially, pull on each other. And since they're participating in this space-time expansion, the pull of gravity exerts a retarding force on the expansion of the universe. It tends to slow it down or decelerate it. So we know that the cosmic expansion has been decelerating due to matter ever since the Big Bang. And since most of that matter is dark matter, 5 or 6 times as much as normal stuff, that's really the cause of the deceleration. However, there's a second entity in the universe called dark energy, which has a very strange property of negative pressure, which means that dark energy accelerates the expansion of space-time. And so it's a countering force to gravity, which will slow space-time expansion down. And thus, at the present time in the history of the universe, we live in an era of accelerating expansion.
Excellent, thank you. Lawrence 4040 has a question about entanglement, and specifically if two particles are entangled, and I observe particle 1 with spin up, and a partner observes particle 2 at the exact same time, will it have downspin? Can you explain how this works?
Yes, entanglement is a mechanism, it's a process in quantum physics, in theory, and then of course in practice, we see it in the real world, where there's coherent information shared between individual subatomic particles. So for example, when two particles that have this property of spin are entangled, then their spin states are coherent. That is, the information is shared between them. And so if an entangled spin down particle is entangled with a spin up particle, it is indeed the case that someone observing one of them will know immediately, or will know the state of the other one that's entangled. So it's a way that information is maintained across a distance. Apparently this information is held instantaneously. In experimental terms, it does not seem to propagate at the speed of light. Entanglement has now been demonstrated not over lab scales, but over hundreds or thousands of kilometers. And this is a truly instantaneous, coherent state of matter between two different quantum states that can be well separated. And yes, if you interrogate one member of an entangled pair, then you automatically and instantly know the state of the other.
Excellent, thank you. The next question is from Aquarius Francine, who asks, where is the dividing line in the universe where time is not ancient time, but closer to our time? Is it outside our solar system or galaxy?
It's an interesting question, and it really depends on what you define to be ancient. Just to use a practical definition, let's imagine ancient refers to human time. So anything that's less than ancient is time that humans can measure and humans have experienced. The solar system is very small light travel time, so it's just hours to the edge of the solar system, and maybe days to places like the comet cloud and so on, or weeks. So this is obviously very recent. If you define ancient time as to be before human civilization, that's something like 10 or 12,000 years. And 10 or 12,000 light years takes you actually only a modest way out in the Milky Way galaxy. The Milky Way is 100,000 light years across the disk. So that's 10% of the galaxy is encompassed by that, or only 1% of the surface area or stars in the disk. If you imagine ancient to be the entire history that humans have been around in any form, then that's more like 200,000 years. And 200,000 light years does, of course, encompass the entire galaxy. So basically, the simple way to put it would be that non-ancient light is light that comes to us from anywhere else in the galaxy, and ancient light is light that comes to us from other galaxies.
The next question is from Jorge Raujo, who sent an email. And Jorge would like to know if you can suggest maybe 2 required reads, like books that you think are required reading for beginner astronomers or astronomy enthusiasts.
Sure. For basic level astronomy, the book that was based on the second Cosmos series, the original Cosmos series by Carl Sagan, and the book that arose from it in the late 1970s are also excellent. But of course, astronomy's moved on. So Neil deGrasse Tyson rebooted the Cosmos series with the cooperation of some of the people who were involved in the original series, not Carl Sagan, who regrettably is dead, but the producer, his second wife, is also from the first series. So that series and the book that resulted from it, called Cosmos, with the author Neil deGrasse Tyson, that's an excellent first book, I would say. And for a second book, I'd go in a slightly different direction. There's a book that's that originally came out 25 years ago, was updated in the last decade. It's about the history and philosophy of astronomy, and it's a sweeping and beautifully written book by Timothy Ferris called Coming of Age in the Milky Way. So to get a full sense of the subject and its deep and rich history, I really recommend, and I've used in one of my classes, Coming of Age in the Milky Way by Timothy Ferris.
Excellent. The next question is from one of our live participants who would like to know, are gravitational waves lensed in the same way as light is lensed?
It's a very good question. And the basic answer is no, they're not. Gravitational waves are ripples, if you like, in space-time, or perturbations or disruptions in space-time caused by gravity, caused by mass changing or mass configuration changing. And space-time does not itself have the intrinsic property of focusing or defocusing radiation that passes through it, including space-time ripples like gravitational waves. So as far as we know, gravitational waves cannot be lensed or bent or focused or defocused by the shape of space-time.
And so this is kind of a related question. MadMel1 asks, the term mass in astronomy seems kind of complex. It goes from giant things to like tiny things like neutrinos. So can you talk about, do you have an elevator pitch or a quick explanation to help people grasp the concept of mass?
Sure. I mean, in an intuitive level, at a gut level, mass is just stuff. It's the material universe. And in the most simple form, mass represents particles, subatomic particles, atoms, and their constituents, because everything in the universe, planets and people and stars and galaxies, are made of atoms. So at some level, mass is just conglomerations of atoms into larger objects throughout the universe. But there are other things that can have mass too. For example, neutrinos or other subatomic particles that are maybe rare. They may decay, so not always continue to exist except for short periods of time, and they have mass. The other important distinction to make, or thing to remember, is that mass and energy are equivalent. Equals mc squared, a famous equation from Albert Einstein early in the 20th century, essentially says that every amount of energy has an equivalent mass. and vice versa. Every amount of mass has an equivalent energy. So when you're doing the census, if you like, or when you're summing up the mass in a universe or any part of the universe, you actually also have to include the energy in that part of the universe and its equivalent mass defined by E equals mc squared. Now, generally in the old and cold and large universe, the energy in any region of space turned into mass is a tiny fraction of the mass in particles and stuff. But occasionally, and in some parts of the universe and in some parts of its history, that's not been the case.
The next question is from a live participant. SSXB asks, could you please explain astrochemistry? And do you have any examples of astrochemistry and the kinds of things that are studied in astrochemistry?
Sure. Astrochemistry is a subfield of astronomy, but it's a very active and dynamic and interesting subfield of astronomy. It's basically relating to the chemistry of space, of the universe beyond the Earth. We're familiar with how chemistry operates on a planet like the Earth, and we think chemistry will operate similarly on other planets. But chemistry also operates in the voids of space, in molecular clouds, in deep regions where stars are forming, and in essentially in places with very low densities, which is surprising. So astrochemistry is the subject of studying all these environments where chemistry may occur. And to give an example, the interstellar medium, the thin medium between stars that has a density of about 1 atom per cubic centimeter, so incredibly low density compared to the air we're breathing. The interstellar medium now has over 100 different molecules that have been identified in it. And those molecules include familiar small molecules, small number of atom molecules like hydrogen sulfide, carbon dioxide, carbon monoxide, methane, etc. But they goes up to molecules that have 13 or 14 or 15 atoms. These are complex hydrocarbons, simple fats. So these are very interesting molecules to find in deep space. And so astrochemistry is the subject of understanding how those molecules came to form, how they got there, and how they interact, and how maybe complexity can be built even in very low density regions of the universe. The principal tool for astrochemistry, apart from lab studies and theory, is radio and infrared or far infrared spectroscopy, because we typically look for the behavior of these molecules, their rotation and vibration states, do transitions at very low energies or long wavelengths. And so spectroscopy at these long wavelengths is how you diagnose what molecules are present in a diffuse region of space.
Excellent. The next question is from an email. Wendy Traver asks, has the Drake equation been updated recently to reflect the growing number of discovered exoplanets?
Yes, the Drake equation has had various modifications over the decades, and especially in the last decade. In particular, it's sometimes been modified by people like Sarah Seeger at MIT and other astrobiologists to really home in on the number of habitable planets. Because of course, the Drake equation includes a set of factors, the last few of which in the product are completely unknown, which is the odds that life forms given the right ingredients, the odds that intelligent life evolves given life of any kind, and the odds that that intelligent life develops technology of any longevity. We still don't know those factors. So people have recast the Drake equation to codify the knowledge we do have on the incident rate of planets and the fraction of those planets that are Earth-like and their potential habitability, so that at least we can refine the equation to put that actual measured astronomical information into one term. And then all the other uncertainties are sort of bundled into another term. So there are simplified forms of the Drake equation which neatly separate out the things we do know because we've learned about them in the last few decades with exoplanet research, and the things we still don't know. And actually those things may be very hard to measure.
We've had a couple of comments about the recent UFO article that you both sent out to the course and shared on social media. People say that they found it very interesting, but I'll post the link in the chat so other people can check it out. But could you just talk a little bit about that article and the kinds of things that you talked about, and and your thoughts on the sort of current version of UFO hysteria.
Right. So, I mean, I'll sort of answer this as two separate questions. The first question is, what's my consideration of UFOs in general? And then I'll talk about the more recent news stories and so on. In general, UFO stands for unidentified flying object. There's a long history of UFOs, of course, in the United States, dating back actually before Roswell, which is 1947. That was a famous incident of what actually was found to be a military weather balloon or high-altitude weather balloon that crashed in New Mexico, and people saw it and thought it was an alien spacecraft. But UFO sightings have been made before that, and they've been made around the world, not just in the US. And so for decades, people have wondered whether some of these sightings are alien spacecraft visiting us. And the consensus amongst most professional scientists and particularly astronomers is that while they don't rule out the potential for alien spacecraft visiting the Earth, they think that the odds of it happening in general are low, and the odds that it actually has happened are incredibly low because the evidence is weak. And why do they think the evidence is weak? Because most of the evidence is either anecdotal, and that's just a tricky form of evidence. You're never going to convince a scientist of a profound implication of a hypothesis that aliens have visited the Earth with purely anecdotal evidence, or it's the quality of the data is insufficient to be sure what the single interpretation is. And that's typically true of photographs, or in the modern era, digital images or digital movies. So this is the consensus view of astronomers. There are obviously some fraction of UFO sightings that are a little puzzling, and they remain unidentified. It's not clear what they are. But astronomers are simply loath or unwilling to automatically or quickly connect the dots to say it must be alien spacecraft, because in practice, there's so many more mundane explanations for most UFO sightings. So to answer the question about the recent fervor and furor around UFOs, this dates back in the United States to 2017, basically, when three Navy videos were leaked to the New York Times, I think, was who published them first. And these Navy videos, purported to show strange objects moving in difficult to explain or perhaps in physically impossible ways, as imaged by infrared, optical, and occasionally radar sensors on these fighter jets. These videos were then officially released by the Navy. They'd been leaked, but they were officially released in 2020. And after that, Congress got into the act and decided that there was something that had to be done about this. There was an explanation needed, and they told the Department and the Office of the National Intelligence Advisor to come up with a report. And so working with the military, there was a UFO report, and I've commented on this in the media and in a few articles. The report was very disappointing. It was 9 pages long, talking about 130 or so sightings over 15 years, and it definitively was unable to categorically classify any of them, except one of them was a weather balloon, a deflating weather balloon. It didn't talk about aliens visiting. It didn't talk about, even use the word UFOs, because the military have rebranded this phenomenon as UAP, unidentified aerial phenomena, in a sense to get away from the stigma attached to UFOs. So the field hasn't really moved forward. And in fact, several commentators and people who understand the technology involved in these sensors have said that these videos could easily have fairly mundane explanations that don't involve extremely rapid rates of motion or impossible motion, and then definitely don't necessarily involve alien spacecraft. So I would say, for all the attention this subject has got in the last 6 months especially, there's no new information here. There's nothing to convince the average scientific skeptic that aliens are visiting the Earth. More data is needed. It's easy to say that. And in fact, Congress has told the military to come back with more and better data so that it can be a better understood phenomena. The military has its own reason for being interested, because it's a national security issue, regardless of what these sightings and phenomena are. The fact that they're in American airspace, the fact that they're in close proximity to military assets like fighter jets doing their work, and the fact that they could belong to a foreign adversary, that this creates a national security issue or risk. And that's sort of why the military is very interested in this. They're not bought into the idea it's aliens visiting either.
Excellent. Thank you very much. We also want to give a shout out to Zoomies15 for subscribing. Thank you very much for that. Welcome to the Teach Astronomy family. The next question is from one of our live participants who asks, what is the reason for gravitational force between objects?
Well, gravity has been recast through the theory of general relativity of Albert Einstein about 100 years ago into something that is not as easily described now as a force acting between two objects in space. Gravity is recast in this theory as curved space-time caused by the presence of mass or energy. And so with that as the concept, then the reason why objects move the way they do, say when they're orbiting each other, or why an object is deflected by what we think of as the force of gravity, is because the existence of mass and energy curve space-time, and then objects necessarily follow the curvature in space-time. In general relativity, the shortest distance between 2 points in curved space-time is called a geodesic. It's a minimum energy path, if you like, in physics terms, and that's the path that objects will follow. So we no longer think of it in the classic Newtonian sense as a force acting between different objects out in space.
The next question is from, we have two kind of career-related questions. The first is an email from Eliza, who is in high school right now and would like to know, how can I pursue my career in physics? And ultimately, I want to become an astrophysicist. What are your recommendations?
Sure. Well, I'm glad you're interested in astronomy while you're still in high school. And of course, in the United States, astronomy is quite rarely taught in high schools. It's taught in some bigger high schools, and it's taught in particular if a particular science teacher has a keen interest in astronomy and the school lets them teach an astronomy course. So it's pretty unusual. And you may or may not be lucky enough to be at a high school that has an astronomy class. If you want to go in the astronomy route afterwards as an undergraduate, doing a Bachelor of Science degree, then the route most people take, including at my university, is to do a physics or astronomy major. You can do an astronomy major in a department that has a lot of astronomers, so they can teach all those classes. And you will also be taking a lot of physics and math. Or you can do a physics major and then add in a little astronomy along the way, depending on how many courses are offered at your university. So the trick would be to pick a university for your undergraduate degree that has a substantial astronomy department. Around the country, most astronomy departments are not autonomous. Astronomy is typically considered a subfield of physics. So you'll find more typically, a physics department, which may have a high energy physics group, condensed matter, plasma physics, etc., and it may have astrophysics as one of the groups, and that's where the astronomy will live, and that's where the teaching of that subject will live. That's a more typical situation. But if you really want to be astronomy focused and say do an astronomy major, then your choices are much more limited because there are not that many universities that have an astronomy major. We do, and we have a large number of majors, 150, I think, at any given time. University of Washington has an astronomy major, University of Texas at Austin, and I'm not going to give a full list, but those are three of the biggest. And so that's your best bet if you really want to do astronomy and you already know that. You will be taking a lot of physics and math too, and you may have the chance of a double major with physics in it, which is a useful thing. It makes you more employable at the end of your degree if you decide not to go into research.
The next question is from Pankashaw, who asks, or says, I'm a healthcare worker, but I'm highly passionate about astrobiology. Can you talk to us a little bit about astrobiology and how one can acquire genuine knowledge about it?
Well, obviously starting close to home, Matthew and I have a MOOC on Coursera, which is an astrobiology MOOC. And I recommend that, of course. Some of you may have encountered or done my astronomy MOOC, but we also have an astrobiology MOOC, which was done more recently. It's only a couple of years old now. So that's a way of getting a very good base of information about astrobiology. And there are other astrobiology MOOCs, massive open online classes that I would recommend. There's the University of Edinburgh also has one in Coursera. I can't remember at the moment what the name of it is, but the professor is Charles Cockle. And there's one that's about to be launched, I think, by Charlie Lineweaver in Australia. He's at the Australian National University, and that I know I watched the making of that course from a distance, and I know that's going to be a good course. So there are astrobiology MOOCs. There are, of course, astrobiology formal programs. We have an astrobiology minor and major for undergraduates at our University of Arizona, and there are others elsewhere. University of Washington, again, is a strong player in the astrobiology field, and they have the same thing. So you can do degree work in astrobiology, but it's typically combined with astronomy or physics. It's not a standalone full degree on only astrobiology. So I'd say online class is the best way to go to just increase your knowledge. Eventually, if you really want to get into it, NASA is one of the biggest employers of astrobiologists, and they have internships. And those internships don't always have to be just for undergraduates. They can be for more experienced or senior people, or people at different stages of their careers. And so that's a possibility too.
Excellent. And so that kind of answers the question, the second question, which is, can I ever, as a healthcare worker, contribute to the field? It sounds like it's mostly a research field, and so that's the avenue that someone could pursue to get involved. Is that correct?
Yeah, and so for someone with a healthcare background thinking of astrobiology, there's some synergy there, there's some relationship there, because astrobiology is a broad field. It's obviously about the study of life in the universe, or the search for life in the universe, but it's also about life on Earth and the history of life on Earth and how it evolved and how different biology might be in other situations. And some of the medical knowledge that a healthcare worker would have is in the biology realm. So it's not out in left field, if you like. But learning astrobiology means you pretty much have to go back and learn some foundational biology and some astronomy and some physics and geology actually too.
Merlin 687 would like to know, what role do people with computer science majors play in the field of astronomy and astrophysics?
They play a very big role actually, and the role is just increasing over time. Astronomy has always had a computational side. So as computers grew in power and capability through the 70s and 80s, desktop computers became more powerful, supercomputers became smaller and even more powerful. Astronomers have always been in the vanguard of using those computational capabilities. So it's a computing intensive field to do simulations of the universe, or how galaxies form, or the way stars form, or how gravitational waves are produced, or how black holes behave. All of these need very intensive computation. And computer science skills are required to do this programming. These are very specialist skills too. They're often using programming languages and methods of parallel processing. For example, you have to be able to program for parallel processors, because that's the kind of computations you're doing. They're quite specialized. So computer science skills have always been used in astronomy, more increasingly, and they're high-level skills that are required. So computer science undergraduates, majors, and also people with computer science PhDs, and even career computer scientists are now involved in research groups doing astrophysics. And that trend will increase. It's not a huge amount of the astronomy field in terms of fraction of the total jobs, but I would say it's a significant fraction, maybe 10% would be a guess.
Then related to that, also, Miriam Bilal would like to know, what programming languages are important in studying astronomy and physics, and what are their uses?
The one that is getting the most heavy use and is part of our undergraduate training is Python. So C, C++, and so on, those are core programming skills that most people have. But there's a lot of scripting and a lot of use of Python in almost every field of astrophysics. Also, the computational landscape of astrophysics and astronomy, obviously many people in their desktops and personal lives are using Windows machines or Apple computers, Windows OS. Knowing Windows or Mac OS is not as essential a skill in many ways in research as knowing Linux and Unix. So those are sort of more stripped down and much more efficient ways to put together a computer box to do the kind of calculations astronomers do. So those are languages that get heavy use in astronomy.
One of our live participants would like to know if two black holes of the same strength and size happen to move close together, where they try to devour each other, what would happen?
Well, we know what happens now. There was a theory of what happened that's been worked out in very simple theoretical terms decades ago, and in more detailed computational simulation forms in the last 10 or 20 years. But now with the detection of gravity waves, we've actually seen black holes merging. So we know what happens, and then we know what the results are. We can't see it up close, though. And so the simulations still guide us as to what it actually might look like if we could see it up close. But basically, when two equal mass black holes approach each other, they're unlikely to have a direct collision. The odds of that are very low. So typically, they're going to have a glancing trajectory where they go into orbit of each other. And then that orbit will gradually decay. And the reason that orbit decays and is not a stable orbit is the emission of gravitational radiation or gravitational waves. So there's an in spiral, which happens very quickly, in almost a crescendo, as the black holes get closer and closer together, and they speed up in their orbit of each other as gravitational waves are carrying away the orbital energy, allowing them to go closer and closer together. And at some point, they reach the point of merging or coalescing. And at this point, the distortions to space-time become extreme. And these distortions are time variable, and that means a lot of gravitational waves or gravitational radiation is produced in the merger of event. And then the aftermath of the merger event is a settling period, or wobbling, if you like, or oscillation, where the merged black holes, now having the combined mass of the two original black holes, settle down in a sort of ringing of gravitational waves and space-time oscillations that persist for some time afterwards. Now, in the math of black hole mergers, when two equal mass black holes merge, the resulting black hole is not quite twice the mass of the two equal sized black holes. It's twice their mass minus a significant percentage that is released, that mass is released as pure gravitational radiation.
The next question, there are actually several questions about the edge of the universe. So we'll start with Loriella Martina, who asks, if the universe is expanding, what is the border between universe and not universe?
That's a good question. And operationally, we don't really know the answer, and we don't actually have a simple answer. All we can do operationally or observationally is say what the limit of our observation is, and where do we see an edge to the universe? And the answer to that is no, we don't. We don't see an edge to space-time. And that's because the universe has a finite age. And as far as we can see with our telescopes, is a look-back time or light travel time corresponding to the age of the universe since the Big Bang. That's 13.8 billion years. And so that's the edge we see with our telescopes. In other words, when we look out in space and therefore back in time, we don't run out of space and find an edge in space. We run out of time and are looking back towards the Big Bang, and so we run out of time. So that's the real answer to the question about the edge.
And then the next question is from, I'm not sure how to say this one, QUTOXZ22, would like to know, so then what would happen if you threw a rock into space and it went all the way to the edge of where it's expanding? What would the stone find? Would it hit some magic wall? Or is there something at the edge of space?
So that's a good question. And actually, maybe the person asking the question knows this, but you're echoing a classic question asked by one of the ancient Greek philosophers. There's a man called Archytas. I think that's spelled Archytus. He was a colleague of Plato. So we're talking about the 3rd or 4th century BC. And he was a famous philosopher. Very little remains from these people. Not much of what they wrote comes down to us. But in a commentary, I think written by another philosopher, Archytas is supposed to have posed exactly that question. If I go to the edge of the universe and I hurl a swift spear, he's just using the kind of metaphors and tools available to an ancient Greek, Do you imagine that the spear fly swiftly and then on forever? Or do you imagine that it hits a barrier and bounces back or breaks? In Archytas's mind, there are only these two options, and that's pretty much the way the question is framed. The answer to the question is we have no sense of a boundary or a physical barrier. So we do not think that a stone or a spear or any object hurled through the universe towards what we might think of as its edge will reach a barrier, a fundamental limit. And you can see the logical problem, which was well known by the Greeks, that if there's a boundary or a barrier or a wall, well, what's beyond the wall? Because the universe is everything there is. And you can't have a barrier or a boundary without asking what's beyond the boundary. Nothing? Well, what does that mean? So logically, there is no boundary. There's no wall that we found. And basically, the object thrown into space will just continue to travel out through space-time, as far as we know, because we've seen no end of space-time with any of our observations.
So then Tiendat 1601 would like to know, so will the universe keep expanding and changing forever, or will it eventually become a state where there are no more changes and no more increase in entropy?
The future history of the universe projected is not completely certain, but some parts of it we do understand. Based on the current state of the universe, the accelerating expansion, dominated now by dark energy, in the future, as the universe becomes bigger and more diffuse and lower density, the influence of mass, normal, and dark matter will diminish. And so, whereas the influence of dark energy, which is causing the acceleration, will increase. So we do not think that the accelerating expansion that we see now will ever be overcome by any force or any other mechanism. In other words, the universe will continue in its accelerating expansion. And the fate of such a universe is interesting because space-time will essentially dissipate. It will just go further and further. All the objects that we see in the universe now, the galaxies we see with our telescopes, eventually they will be carried away from us at more than the speed of light in this accelerating expansion, which means we will stop being able to see them. So the extragalactic universe will be wrenched from view by the accelerating expansion. And meanwhile, within our little piece of the universe, the Milky Way having merged with M31 Andromeda in about 4 billion years, this supergalaxy will settle down, stars will die, they will eventually dissipate. So the future of the universe in this view is a victory of entropy, a disorder. It's the slow dissipation of normal matter, eventually the decay of normal matter, the slow evaporation of things like galaxies, including our own, and then the dissipation of space-time overall caused by dark energy.
Excellent, thank you. The next question is from Zorukal, who asks, what are zombie stars?
Zombie stars are, it's a very colloquial term. I mean, they're stars that do not appear to die, or they have episodic episodes of emission, and then they come back to life again. There are a large number of types of variable stars, and we don't fully understand all of them. I think there are over 30 different types of variable stars. So there are stars that give the impression that they've had their life and finished, and then they flare back to life again or come back to life. But in truth, there is no such thing as a true zombie star. There's no such thing as a star that, having died, comes back to life or stays in some limnic or limbic state. Because when a star dies, its energy source is exhausted and it becomes a stellar corpse, and there's no return from that.
So then the follow-up question is it possible, do you think, to have planets around these stars or to have life on planets orbiting these stars, and what would that be like?
So the general question of can you have planets and or life on planets around dead stars or stars that have episodic normal emission and then fade? And the answer is yes. Obviously, the star has a source of energy, but the gravity will not change unless the star loses mass. And so planets around stars like the sun in the middle of its life will continue to exist and orbit a star like the sun after it's died and become a white dwarf. The orbits will actually change at that point because the sun will lose about 1/3 of its mass in the planetary nebula and red giant phase and leave behind a smaller stellar corpse with weaker gravity. But generally, planets can survive this. Now, life surviving it is a different matter entirely, around dead stars or stars through episodes of their emission where they're not uniformly fusing hydrogen into helium on the main sequence. Life, unless it's extremely well buffered from these episodes of the star, will probably suffer badly, and you'll not have a habitable zone that can tolerate life. The only exception will be on a planet where the atmosphere creates an entirely self-contained environment where the energy is provided perhaps by geothermal energy or geological energy of radioactive decay, and no stellar energy is needed to sustain the life.
The next question is from one of our live participants. Why do scientists expect quantum information to be preserved at an event horizon if space-time is so distorted around a black hole? Wouldn't that sort of naturally sort of screw up or dissipate the information?
The preservation of information, quantum information near a black hole or in extreme situations of space-time is a genuine research topic where the answer is not known. And that's simply because we do not have a theory that reconciles quantum physics with general relativity, our theory of gravity. So at some level, there's no answer to that question. It's just speculation because our theories are inadequate to describe the situation. However, inasmuch as quantum theory is very well tested and very well proven, the preservation of information in quantum interactions always holds in the lab. And so people think that it should also hold in the situation of a black hole or an event horizon. And that's created the situation of what's called the information paradox, the inability to resolve this distinction between quantum physics and its predictions and general relativity. And so there's an active research field there, and with no simple answer to the question, unfortunately.
Supreme Mouse would like to know, can photons arrive to Earth in a different sequence than they left their source?
Yes, definitely. And gravitational lensing is the main reason why. If photons came from a source and traveled simply through uniform and linear space-time, then their arrival times would be just dictated by their departure times, just simple. But in a situation of curved space-time, then different things can happen. And gravitational lensing is a good example of how. So for example, in a gravitational lensing situation, you have a background source of light, maybe a quasar, some intense light source, and the light can take different paths around an intervening galaxy and be lensed by that galaxy. Now, it's very easy in these situations, and it happens routinely in astrophysics, hundreds of examples are known, that light passing one path around the galaxy has a longer path length and therefore a longer travel time than light passing on another path. So it's definitely the case that in gravitational lensing situations, the arrival order and timing of photons is strongly affected by the lensing geometry. If you know the lensing geometry, this is all very predictable. But it's a very interesting phenomena indeed. And the time travel delay of photons in a gravitational lensing situation is actually used in a very clever way by astronomers to measure the Hubble constant, which is the expansion rate of the universe at these large distances.
The next question is from Autisam HAQ. How could nothingness form our universe? Is that acceptable? Shouldn't there have been something before the Big Bang?
Well, it's a philosophical question at some level and a semantic question. The physics of how nothing can lead to something is grounded in one phenomenon that does have a place in modern physics and everyday physics, in lab physics, and that's the idea of vacuum energy. The idea that the vacuum is not nothing, as we might think of it, but actually has the potentiality to create particles and antiparticle pairs, which in turn means it has the ability to create energy. So the fact that the vacuum has energy is one of the mechanisms by which you can have an expanding region of space-time resulting from that energy. You can have the creation of particles and antiparticles resulting from that vacuum energy. So we do have a mechanism in fundamental subatomic physics for how you can get something from nothing.
The next question is from Sarcastrophe 143. What would be the velocity of a galaxy so that its light fails to reach us due to the expansion of space?
Well, it's all referenced to the local speed of light, to the locally measured speed of light. Photons measured in any inertial frame, which is any sort of reference frame where you can synchronize clocks and measure the sequence and timing of events, photons are always observed to travel at 300,000 kilometers per second. Space-time, however, can be expanding, and it's the medium through which these photons travel. So there are places in the universe we can look out to, and it turns out in terms of a redshift for a galaxy, that's the amount by which the waves are stretched by the expansion of space, at a redshift of a little over 1, I think close to 1.5. So by the time the photons have been stretched by a factor of 1 plus z, which is 2.5, over the travel time to us, that corresponds to a place where when the photons were emitted, that space where that galaxy is was moving away from us at the speed of light. And so we know of many parts of the universe. We've seen many galaxies with that redshift, many galaxies where the light we observe now was emitted when that galaxy was moving away from us at the speed of light. So it's a pretty routine thing in cosmology to have such a situation.
All right, we'd like to do another shout out to Zarukal, who subscribed. Thanks so much for that. These subscriptions really help our channel. They help us grow our channel. They help us keep folks on our staff so that we can keep doing these live sessions and courses. So we really appreciate it. Shema98 asks, the color of a star is the color of the star on the surface. Does it change with radius since the Planck graph depends on temperature?
Yes. So the color of a star indeed represents what we see as the surface, and astronomers refer to this as the photosphere. It's not a physical surface. It's not a hard edge, a boundary that you would bump into if you ran into it. The edge of a star is just a slowly decreasing density of plasma. And what we see as the surface just represents the region at which photons no longer interact with electrons typically on their way out and come straight to us in straight lines, and so we see an edge. That's the photosphere. And the temperature of that is just under 6,000 Kelvin for the sun, and it's different temperatures for other stars. And indeed, with radius, that temperature does change. So as you go into any star, the interior of any star, including the sun, the temperature rises steadily. And so if you were inside the star, the photons bouncing around in an opaque situation would be hotter and hotter and shorter wavelengths. And so yellow photons that we see from the edge of our sun going further in would suddenly be blue photons and then ultraviolet photons. And by the time you got to the place where the fusion's occurring, the central quarter of the radius of the sun, the temperature's millions of Kelvin, and so these are X-ray photons.
The next question is from Daya, who asks, what do you have to say about the claim that has been made recently, but it was really a year or so ago, about phosphine found on Venus, which apparently points towards possible extraterrestrial life? What's the status of that discovery?
The status of the phosphine on Venus discovery is that it's mostly gone away, not entirely, but mostly. And it's gone away in two senses. First of all, it was a very difficult detection, a spectroscopic detection of a signature of this one compound in a very messy part of the spectrum. And it turns out that the group that published the first result overestimated the strength of this spectral feature, which means they overestimated the abundance of phosphine in the atmosphere of Venus. And that's just because this phosphine feature was confused in the spectrum. It was adjacent to or almost at the same wavelengths as features from other unrelated molecules. So that was just a mistake, if you like, but a difficult thing to do in reducing the data. And the second is that it had been assumed, because on Earth phosphine is really only associated with situations of biology, that phosphine is what we would call a biomarker. It's a strong indication of biology at work. In the meantime, geologists and geochemists have come up with mechanisms where you can get very small amounts of phosphine. Again, it depends on how much phosphine there is. And if it's a very small amount, there are ways to get phosphine at that level without biology being involved. So for both of those reasons, the phosphine discovery has mostly, but not entirely, gone away. There's still something interesting to study there. And in a sense, it's reminiscent of the debate over methane from Mars, another molecule that's taken to be a biomarker. The methane on the Earth, which is definitely associated with biology, is a level of multiple parts per million. The methane on Mars is at levels 1,000 times lower, a few parts per billion. And at that level, once again, it's not always and necessarily associated with biology. There are geological mechanisms for generating modest amounts of methane. So it just underlines how tricky this whole business of finding biomarkers or spectral indicators of life really is, because there's usually ambiguities and the interpretation is sometimes not easy.
All right, thank you very much. The next question is from one of our live participants who asks, I'm sorry, I got mixed up in my, so what additional, Yankow asks in reference to an earlier question, gravitational waves are a key technology to make advancements. Can you talk about what fields or discoveries or areas gravitational waves are going to help us make advancements in the field of astronomy, and what kinds of things we can explore now because we have access to gravitational waves?
Well, with better gravitational wave detectors, which are coming pretty much every year. So in addition to the two LIGO instruments in Louisiana and Washington State, there's the Virgo instrument in Europe. There's an instrument that's coming online in Japan. There's one in Brazil. There's one in India. So there's a whole network of gravitational wave observatories, and they're going to work in concert together to pinpoint with greater accuracy the direction for the waves come from and have better sensitivity. With those capabilities, we'll have industrial scale measurement of black hole mergers. We'll see large numbers of black hole neutron star mergers and neutron star mergers. And we're going to learn a lot, for example, about neutron stars that we didn't know. That's beyond what we're already learning about black holes. These instruments will also detect supernovae. Supernovae explosions are not usually totally symmetric, and the distortions of space-time that result in the explosion produce gravitational waves. So we'll get signatures and information about the very incredible tiny fractions of a second when a star collapses and the instantaneous temperature rises to billions of degrees. That'll be exciting. And then the other prospect, which is very exciting, but it's very hard to predict what it's going to look like, is that we may be able to see gravitational waves from the very earliest instances of the universe after the Big Bang.
Excellent. Thank you very much. It's now 11:01 our local time. We'll go a little bit longer since we got started a little bit late, but I don't want to hold you up, Chris. So if you need to go, then we can go. The Black Tulip, okay, the Black Tulip 18 would like to know, to what extent does philosophical thinking aid advancements in astrophysics?
That's a good question, and I think it's significant. Remember, for example, that until the 70s or 80s, physics, which is the foundation stone of astronomy, if you like, which is really astrophysics, physics was called natural philosophy. And so the relationship between fundamental science and philosophy is pretty strong, because scientists doing physics or astronomy are asking profound questions about the nature of the universe and our existence and our perspective and our role in space and time. And so philosophical questions are entirely valid. What came before the Big Bang? What is the meaning of there being life in the universe beyond the Earth? And also even how to approach the subject. Philosophy sometimes helps us understand what are questions we can plausibly answer and questions that we may not plausibly answer. Philosophy also helps astronomers, among other scientists, from thinking correctly and logically about how to approach their evidence, about how to interpret their evidence, about how to do, for example, thought experiments. These are essentially tools of philosophy whereby something that you aren't actually able to do in the lab or with a telescope, you propose, you hypothesize an experiment that you describe conceptually, and then you follow through the implications of that conceptual experiment. That's pretty much a philosophical exercise, and it's very useful in astronomy and other subjects too.
All right, and then a quick update for everybody. We will pause for just a couple of minutes after this session. Actually, we may go right into it, but we're going to have an astronomy news session with two of our students who are going to go into sort of recent astronomy stories as soon as we're done with this. And we will take one last question, who's from Sharon, who asks, do you think that extraterrestrial life might be in the form of microorganisms instead of humanoid forms as we perceive them after watching movies?
Yes, I think that's very likely. And in a sense, science fiction movies and the popular culture have conditioned us a little too much to expect humanoid life forms out there. I think that's a very anthropocentric point of view. There's no reason to expect advanced life forms will look like us at all. So logically, the first forms of life on the Earth, the forms of life that were on the Earth for most of its history, and still in genetic terms, the most abundant forms of life are microbes. So logically, the same should be true of planets elsewhere. So we generally will expect the microbial universe to be far wider, more abundant, and more prolific than the universe of advanced creatures like us. That's just a logical and sensible conclusion to draw from the experience of the Earth. Of course, as we speak, no life has been found anywhere, but most of the active experiments, except for SETI, are actually trying to look for the influence of microbes on a planet where the influence is sufficient to alter the atmosphere of the entire planet. We can't detect microbes individually on exoplanets, of course, and we probably never will. But if those microbial species are abundant enough to alter the ecosystem of the planet, then we may be able to detect that, as they did on the Earth when they injected the oxygen we breathe into the Earth's atmosphere. So that's the path that astronomers are trying to use to show that we live in, say, a microbial universe. Thanks for the questions. Good variety as always, and some new topics even. And I'll just close there and thank Matthew and Vicki, and we'll hand over to the next session.
Excellent. Thank you all for joining us. We really appreciate it. Take care, and we will see you all next time, which will be in about 2 weeks. Check the calendars, and we'll send out announcements. Take care, everybody.